here's where we begin. You get this, this equation that you need to satisfy. There's your polynomial. And then they introduce this idea that alpha is this complex root of this equation. So alpha is not real. Okay, so we know that. Or at least it's not solely real, it's got a real part, imaginary part, which comes in later on. Okay. And then it says, if that's what alpha is, it's a solution to this, then let theta equal, and then there are these weird, like seemingly random, I think it's like alpha, is it squared?
Yeah.
And alpha 4,
Yeah.
and then phi, which is these other powers of alpha. And you're like, what on earth is that about? Okay? So, then the next part says, show that, and they give you this result. So this is what we're required to prove. This is where we're headed. We want to get some relationships between these two, whatever they are. Okay, so I think it was that the sum is -1,
Yeah.
and the product is 2. Is that right? Yeah, cool. All right. So what do you do? Where do you even begin, right? So we're going to go back to, like, let's think about this for a second, right? See this and this line, they're just defined, okay? So they don't really give you any interesting or valuable information. But these two, these are kind of like facts, right? It's like, look, I can tell you something about alpha. It has these particular qualities. It's a solution of this polynomial. And this polynomial also is a, look, that's a fact. This is known, and you can then conclude things from it, okay? So this is kind of the important part here that we're going to build off. These are the facts, right? There's nothing, you can't build anything off these because these are just labels, okay?
Oh.
So we're going to get to these, but when you think about, like, a question gives you all these different things. When they say let, right, this is kind of arbitrary. They could have been equal to different things, right?
So you should start from, like, the
Yeah, they're not going to give you a helpful starting point. You'll just go round and round in circles because these aren't giving you any information, okay? It'd be a little bit like when you get a circle geometry question, right? Something like this, and you're like, okay, here's an angle, I'm going to call that alpha, okay? Now, this doesn't give you much useful information at all. Like, I can't draw any conclusions from it. But if I told you all of a sudden, for instance, that, you know, this is badly drawn, but suppose I said, look, that goes through the center, and then I gave you like a sign, it's like pi on 6 or something like that. You're like, oh, this is a fact. I can deduce things from this. You can't deduce anything from that because it's just a label. You could have called it that or that or anything, right? Which is the same thing here. So we're going to bring this into play later, right? But it's not a good starting point. So therefore, here's where I'm going to begin. Z to the power 7 equals 1. Now, that's good. That tells you that this is going to have something to do with the fact that, remember how alpha is it's the smallest argument, right? So therefore, if I were to draw a diagram, right? So you draw yourself a little diagram here. So this means that if I take alpha, right, which should satisfy this equation, right? If I raise it to the power 7, I should end back at 1. There's 1 there. Okay, so in other words, if because multiplication by a complex number is rotation, yes? So that's why your diagram looks something like this. I can't remember, but something, you know, like that, like that. You know, yeah, that's exactly right, right? So that means that if I go around 7 times, okay, that's going to bring me back to 1, okay? Which tells you that the size of one of these angles, being that the whole revolution is 2 pi, right? Then the size of one of these angles, and it's the smallest one, should be 2 pi on 7.
Yeah.
Okay, so that's useful, and we'll come back to that. You can have a look at the later parts of the question. You can see that 2 pi and 7, 4 pi and 7, it's clearly related somehow, okay? But the question is how, right? Okay, so you note that, you're like, okay, I'll get to that one later. I need to do something which will bring in all these extra powers of alpha, right? So clearly, you notice, like, it goes alpha to the power of 1, 2, 3, 4, 5, 6, and then it stops. So that gives you a clue that, okay, these powers, they must have something to do with this power, right? Because they stop at 7, as it were, okay? Like it doesn't stop at, say, 3, and it doesn't stop at 10, it stops just shy of 7. So what do they have to do with each other, right? So this is a bit rabbit out of a hat, this part, but I'm trying to show you why there are clues that lead you to this point. I'm going to rewrite our polynomial like this. Same thing, right? But the reason this is useful is I can factorize it. Now this is not a common kind of thing to factorize, right? You don't see this kind of thing very often, right? What you do see, results that you do know are, say, difference of squares, right? So difference of squares we know how to factorize. Z minus 1, Z plus 1, okay?
Because I did it. I
Yeah.
did cube one yesterday.
You can do cubed, right? We did learn, like in year 9 and 10, you learn the sum and difference of cubes, okay? So we were supposed to, okay? So therefore, oh, sorry, because you came here in stage 6. Anyhow, we can factorize this. So there's a mnemonic for this, by the way. I don't know if you've ever learned it. This is a very specific case. The general case looks like this. Here's the difference of cubes, and here is the sum of cubes. Okay. So the way that you do it is they both have the same structure. So this is how you can remember it, right? So you're going to get A, B, A squared, AB, B squared, right? And it's going to be the same for each one. The trick is just to remember where the signs go. So the mnemonic that you use to remember it is SOAP.
Oh, really?
Okay, so the signs work like this. There are 3 signs, right? 1, 2, 3. You fill them in by saying the first one's the same, the next one's the opposite, and the last one is always positive, no matter what. Okay, so look at this. Minus, same, opposite, always positive. And the same thing here. So same, opposite, always positive. Okay, so that's how I remember that, because it's quite fiendish to get all the signs right.
Sometimes I go back and I'm like.
Yeah, you can expand it out. Obviously, it's like, okay, good, yes, I'm sure, right? So obviously that works, but a bit time consuming. So in a pinch, this will work for you. Now we've got a difference here, so I'm just going to get rid of this guy. And you'll also notice that my B is 1, which is kind of neat, right? So here, I should have, this will be Z minus 1, right? Now, what happens in here? I'll have A squared, right? So it's going to be Z squared, plus AB, which is Z times 1, which is just Z, plus B squared, which is 1 squared, oops, plus 1. Okay, there you go, right? Now, this is interesting. Now I can get rid of this. Clearly there's a pattern happening here, isn't there, right? And you can almost guess what would happen if you would have Z to the 4 minus 1. You'll still be able to take out that Z minus 1, right? Just following the pattern, what would you guess? What would you expect to get from this? Yeah. Z cubed, and then there will be a Z squared, and then there will be a Z, and then there will be a 1. And again, you can test it out by expanding, but you can kind of see how it's going to work. Watch this, right? You get this Z and that Z cubed, and they'll become a Z to the power of 4. Tick, right? Now then when you pair up this guy with this guy, you'll get a Z cubed, and a Z squared, and a Z, right? But then you're going to subtract all of those, and you'll be left with a minus 1 hanging at the end. So you can see that I can generalize this. I can generalize it as far as I like, okay? And now you can see where this is coming from, okay? So, I'm going to say this is true, okay? But alpha is a solution of this, right? Or alpha satisfies this equation. That's what it means that alpha is one of the roots, okay? So it makes that work. So that means this is true. Okay, and now I'm going to pull out this this factorizing trick, right? So if I factorize it, I should get this alpha minus 1, and because this power is 7, I'm going to start with 1 less, right? Ta-da! Okay, so this will be alpha 6, alpha 5, alpha 4, all the way down the ladder, and that should be 0. Okay, so this is good. Now you have a look at what we're getting towards, right? So this theta plus phi, okay, that's alpha plus alpha squared, alpha cubed, alpha. That's this thing here.
Minus the 1.
Almost. That's right. Huh. That's suspicious, right? But we're not there yet, are we? We've got this guy hanging around. So how do I get rid of this?
Alpha's not real.
Right. Okay. So alpha, since I know it's complex, it can't be 1, right? So I can say, but alpha can't equal 1, right? As it's not real. Okay, so if this can't be 0, then this has to be 0. So that's alpha 6, alpha 5. So this is the first part of part 1 that we needed to prove. That's equal to 0.
Yeah.
So then we'll kick that guy over. We'll replace these by the theta and the phi, which is just the labels. That's equal to -1. Okay, so that's good.
Yeah.
Right, so we've used this quaint factorizing thing. Okay.
But you can't do the same for sum of, I think it was Z to have 7 plus 1.
Not quite, though it can be done. If you think about it, you can factorize it, but it's not as neat. So, and there's another different result for it with alternating signs.
Yeah.
So, but we don't have to worry about that in this case. Okay. Now, where does this go? Okay, so we sort of went from here and then we went down. Okay, and we have this handy result. When you look at this, right? Theta times phi. We know what theta is and we know what phi is, so I can actually multiply these out and I should get something that relates to what I already know. Okay, so I'm going to give that a go and see what happens. So I'm just going to do, what did I write? Theta times phi. Okay, now this looks like it will be awkward and really long, but it's actually not so bad because of how structured the thing is that the things are that we're trying to multiply. Okay, so I've got here alpha squared, alpha to the 4, alpha cubed, alpha to the 5, alpha 6. Okay, now I've got triples so that I don't overwhelm myself. I'm going to do this in 3 lines so that I know I don't miss a term or anything like that. Okay, so I'll do alpha by all of these first, so it just raises all those powers by 1. So I should get this. 7.
Yep.
Okay, so there's the first triplet. Then I'll do the next triplet, which raises them all by 2. So that should be 5, 7, and 8. And then the last triplet. So far so good. 7, 9, and 10. Okay. Now apparently this all boils down to 2. So the answer is, how do I get 2 out of that? Well, you can see a few handy things here, right? For instance, everywhere you see an alpha to the power of 7, I know what alpha to the power of 7 is because it satisfies this equation. So all of those guys are 1. So I'm just going to replace those just quickly now with another color. So I've got, this will just save me rewriting the whole thing all over again. So I've got a 1 here, 1 here, 1 here. That's kind of nice, right? Now what do I have left? I've got an alpha 4, 5, and 6, which is it's kind of parts of this, right? But then you have these higher powers of alpha, and you're like, what do I do with those? Now the thing is, I can do the same thing with those that I did with these. I can take out a factor of alpha to the power of 7, because it's just 1, okay? So this is worth a new line. That's 1, 2, 3, so I'll just write that down. And then I've got my alpha to 4, alpha to 5, alpha to 6. Now what's left is these guys. So I'll take out a factor of alpha to the power of 7 from all of them. So plus alpha to the power of 7 outside of alpha squared, alpha cubed. Alpha squared, alpha cubed, which is exactly the terms I'm missing over here, isn't it? Okay. So now I can just replace this alpha to 7 with a 1. Okay. So now what am I left with? It looks to me like I'm left with this line. See this here. That's if I put them all together, I should get theta plus phi. So that's 3 plus -1, which is 2 as required. Okay. Isn't it so easy when you see the solution? You're like, when you're trying to, obviously I've taken a straight line, haven't I? So I knew exactly where I was trying to head, which is why I can get there so quickly. But hopefully you can see like the clues that I used. For example, how did I know to pull this rabbit out of a hat? Right? It's like, well, I knew I had to get something involving this, right, out of this. Like, where does it come from? It must be factorized. And once you get this result, this one kind of falls out. Okay.